Okay, guys. So it's actually, I'm a little bit embarrassed because it's like almost half of the audience is people from the quantum mechanics lecture I'm sort of having. So you guys already know it, I guess. If you wish to leave, no problem. Just go on. Or maybe you can help me with experiments, which you know already. Okay, so why do we care about the trace? Actually, there was this stuff, why do I care about the trace, but not that I really care. So I changed this to we. But the thing is, so let me start. So what is the trace, right? We talk about the trace. Trace is a property of a matrix, first of all. So if you want to talk about the trace, you have to have a matrix. So it's a fairly abstract thing, generally speaking. But a matrix is just like a square of numbers. There will be different numbers in different cells over here. And the trace is just a sum of diagonal elements. So you probably have seen the poster. Thank you, Daniel. So there is an example. There are some numbers. And trace is a sum of this, just of diagonal elements on the matrix. So when I actually, I stopped here. When I was preparing this presentation, I sort of stopped at this moment, the first slide. Not good, but anyway. It's really, think about it. It's the sum of the elements on diagonal of a matrix. What kind of consequences can that stuff have in physics or in whatever other thing? And then I recall the paper by Wigner, which has this lovely title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It's really amazing that this sort of stuff, so have a read of that at some point if you wish. But indeed, trace does have some meaning in the world around us and some consequences. So the consequences I'm going to talk about are in quantum mechanics, which is sort of my field of study. Quantum mechanics is our basic physical theory right now. That's what we think is the nature works like. And this sort of stuff happens on the micro scale. We learned quantum mechanics when we studied really tiny objects, like atoms, electrons, and things like this. And there, in this atoms, electrons, so if this guy is an electron, this sort of stuff happens on a daily basis. Things can propagate through trees and stuff like that. So actually, quantum mechanics predicts as well that this thing is also possible. It's just really, really tiny probability that this will happen without seriously harming you. So you can try that, but not too much, right? So in order to give you a crash course to quantum mechanics, I sort of thought that I'm going to perform an experiment here. So I brought a quantum equipment. And the quantum equipment is this and this. Do you guys know what it is? Not my students, right? Mathematicians. Who's a mathematician here? Do you guys know what it is? Probably not. It's a quantum equipment. Per definition. Then we can study properties of the quantum equipment. So what this quantum equipment is this stuff is called the polarizer. So what it does, it's sort of, the light around us has certain properties which we can't see. So one of them is polarization. And polarization is, maybe you remember this sort of concept from your high school, I don't know. So polarization is something we humans can't see. It's this property of light that in classical mechanics, at least or electrodynamics, when we describe light, it's described by some fields, electric field and a magnetic field, and these fields change in time. So you have some sort of electric field vector. These are these arrows here. This is supposed to sort of represent electric field. And what light is that this electric field oscillates. So you see it becomes bigger and bigger and bigger, and then smaller and smaller and smaller, then it becomes negative, 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 more negative, then less negative, and so on and so forth. It sort of oscillates. And when it oscillates in one plane, it doesn't have to. It's a vector, 3D stuff, so it can sort of do various things. But when it oscillates in one plane, then we say that the light is polarized. So this device over here is actually doing it. So the way there's something inside it and some sort of molecules which are really, really long, and they will absorb all the light except only light which is perpendicular to these molecules. Or some stuff gets reflected, actually, but roughly speaking, whatever comes through this has this electric vector oscillating in only one plane, like here. So when I have two of these guys, you can sort of imagine what will happen. Especially when they are orthogonal, then, all right, okay. So unfortunately, I should have written here what is the direction of light that actually gets transmitted through this polarizer, but I haven't done it. So here's another polarizer. And the thing is that when you see that the picture is already a little bit darker than just with one polarizer. But when we start rotating it, what will happen is that it gets darker and darker and darker. At some point, really nothing goes through. Try to see me. Can you see me? No one can see me. Try see me now. Well, it's hard too, but it's a little bit easier maybe. It's probably better with the laser. So if you have a laser, of course, it works for any light, right? For the light around us, for the light from these devices. Any light has the property that it's polarized or not. So whatever goes through this polarizer, actually nothing goes through. Maybe actually the light from this guy is, oh, interesting. So we have just learned something I didn't know. The light from this guy is polarized. That's something we can see with our eyes, but with these devices we can learn. Why? Because you see that there is a bright spot over here, and then there is, if I keep it like this, so there is still some light going through, but if I rotate it, there is almost nothing goes through right now, right? So which means that the light emitted from this device is perpendicular to this particular direction of my polarizer. I think you got the concept, right? So this is depolarization, and this is how we describe it in classical sort of mechanics. And so this guy is just a picture of when you have two polarizers, when you rotate them, then intensity of light changes when it passes through. And exactly how it changes is this, with physicists call this a malus law, something known from maybe 18th century or something like that. People were playing with light, is that, sorry, is that when you have your polarizer at one angle, so say P1, it's just vertical, and then the light transmitted through this guy is therefore oscillates, the electric vector oscillates in this plane. And then you have another polarizer rotated by angle theta. What is relevant here is that you take the component of this vector, of this electric vector, along the direction theta. And that is, so the electric field is now E1 cos theta. And what we see is actually the square of this. So this is something which you just simply have to trust me. That's how physicists describe intensities. Otherwise, it would be strange because it would be negative, right? So what the hell does that mean? It's negative. Intensity should always be a positive number. It's sort of how much light gets to your eyes. And negative light would mean, I don't know what, that light goes out of your eyes or something like this. It doesn't really work, right? So we want this guy to be positive always, so we square it. So you see that the thing is that the intensity goes, if you rotate this polarizer, it goes like cosine square. And now, there was nothing quantum here. But in fact, there are other experiments which shows that light, another way to describe light, and actually it's really a necessary way, if you want to be correct, if you want to describe properly certain experiments, you have to look at light as composed as a bunch of tiny, tiny particle-like objects people call photons. And then these photons, so it's actually, maybe let's come back. So the intensity is then proportional to how many photons come to your eyes. It's really sort of just this. Photon is a tiny, tiny piece of intensity, piece of energy. When one photon comes to your eye, you can see it. Actually, frogs can see it, interestingly, but you can't. There are frogs which can really see single photons, amazingly. Then well, anyway. Frogs. So even people have built single photon detectors taking the eye of the frog out. So then 2 photons come, you still can see it. But when 5 come, or 10 of suitable energies, blah, 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 then you can see it. So it's sort of, and then the more photons come, the brighter the picture you see. So the number of photons goes together with intensity, what we perceive as intensity of light, whether the picture is brighter or not, or less bright. And now the trick is that will be my only mathematics sort of, how do I change this? Very sorry for this. So the trick is that the light, which is composed of photons, there will be a trace in a second, It's actually these photons, it's really hard to make them interact. They essentially don't interact. The simplest visualization of this fact is that you take two light sources, like a torch, and you know what happens if, imagine that this guy is turned off. Then there's some light going on like this, right? But then when you turn on the other light, okay, you will have more photons here. That's why you see it's sort of more bright in the middle, because there will be photons from this guy and photons from this guy. But otherwise, they just go through each other and they don't see each other. Photons do not interact. And this is why this stuff is a truly quantum device. Because how do you explain this on this level of photons is that every single photon that comes here, they don't interact. So what we see when we rotate these polarizers here is the effect on every single photon. So when I have a polarizer like this and the light goes in that photons are polarized, so the light of a photon, the electric vector of a photon, you can speak about these things, is polarized like this, then actually what happens when you rotate it is that every single photon will have some chance to go through this polarizer and will have some chance not to go through this polarizer. And we get this cosine square formula for the intensity because simply less photons go through this polarizer. Every single photon either goes through or not, and there is a probability for this photon to go through. That goes together with the overlap between these two directions. Hope you sort of grasp it. Any questions? You can feel free to disturb me. Feel free to ask me anything you wish at any time.
Is it the same kind of stuff that they put in the 3D glasses in cinema?
Almost, but these guys, so this was this kind of stuff which they put in 3D glasses of the old generation. The new generation has actually the right circular and left circular polarization, which is a little bit more advanced. But the basic idea is this. Yeah. Because the thing was that with these guys, I think people were sort of, if you try to fall asleep a little bit on this movie, then the picture really doesn't fit, right? Every photon has a probability to... so people complained about that. But with circular polarization, this problem is actually avoided. Right. So maybe they use some filters, but polarizations as well. So there is really... Okay. Definitely, they look like red and blue. So it's like a filter. So everything. Well, okay, we have to Google it then. Why would that be the case? You send one signal. I don't really understand this, how this 3D effects work. So frankly speaking, but I can sort of imagine that you can send one signal in the light polarized in one direction, and you have another signal in the light.
Basically, put like two pictures, one on top of the other, and then
yeah.
one of the filters, they are a little bit,
takes one of them. All right.
One of the filters gets one, because this is how 3D vision works. So you have two pictures which are a bit misplaced.
All right. So that's okay. So you're saying that it's just with colors. Okay, but in principle, you could do that with polarization, I imagine, as well. Yeah. So, yeah. So, okay, maybe in practice, it's actually just color filters. Thanks. I don't know. No, these are actually not so good because they, as you see, even though I have this direction sort of parallel, but actually the picture, it should be that every single photon that goes through this also goes through this because it's just along the same axis in principle. But it's a little bit darker because they are really not perfect, and sorry for that. So maybe before I get to this trace, so it's like this. So the whole problem of this polarization is that, so we are talking about polarization direction, so in which plane the electric vector is rotating. So when we have a polar vector, say, rotating, not rotating, but evolving, oscillating in this plane, we can call this guy, say, 1, 0, such a vector. I'm just giving it a name. And then a vector which is rotated by this guy from this guy by some angle theta will have a theta component over here and some sine component on some orthogonal axis. And then you can just say that the way to calculate this probability for a photon to go through, one way, is just to simply take an inner product of these guys and square it. That's true. But so sort of that's mathematically how you would get this cosine square. But you can also use the trace. And actually, So now I'm just showing you the calculation sort of which physicists usually do. So the thing is with the trace is that this gives us, generally speaking, trace in quantum mechanics is used to calculate probability of a certain measurement outcome. So in our case is whether a photon goes through the polarizer or not, probability for this guy to go through, when you are given certain initial state, like a photon which is propagating along v day, this vertical day, oscillating along vertical direction. So you can verify that indeed this is the case. And actually what happens here is that we are not using vectors, although we could, but physicists decided to do more complicated stuff. There is a reason for that. And so you can verify that that's actually what happens, that this matrix on the left is just this vector, but multiplied by some other vector, such that at the end of the day you get a matrix. Like, does that work? 1, 0, 0, 0, right? That's the matrix, as it should be. Then the other matrix is just taking this vector and also doing this trick. So let's verify it. The trace of this guy is just element on diagonal. So when I multiply this guy with this guy, this is the cosine square. And then the other diagonal element of the product of these two matrices is 0, because these guys are 0. So it is indeed a cosine square. It's just another way of writing down this, how to get this cosine square quantum probability. And the way why physicists decided to do this in terms of matrices and not just vectors is that I cheated a little bit, of course. And I cheated with the fact that I said that every single photon that goes through this polarizer is actually exactly, polarized along this direction. In practice, this is never like this. Or if you have another polarizer in some distance, there will be some other photons coming from other directions. So you can't really describe it by a single vector. And I will not go here into the details, but if you really want to take into account this more realistic situation, that you don't have perfect polarization here along one axis, but actually there is a little bit of component along another axis, or you want to take into account that photons are coming to your second polarizer also from other directions, then it is necessary for you to use the matrices here. And even in this general situation, the probability to observe certain result is still given by the trace. So this is the reason why we sort of care about the trace, because it connects this mathematical description of quantum formalism into the lab, into the real world. It gives me the probability that a photon gets reflected. In other words, it will translate into how dark this picture is when I rotate this polarizer. How does it change this darkness? Or another way to put it, which Daniel figured out, it's pretty cool, is that imagine so you can also think about this trace as a probability that when you insert this matrix, or this state to some measuring device, this is what will come out. So just recall this stuff again, right? So after this filter, there is supposedly a photon in this direction. But after this filter, it has to be consistent with the second polarizer. And this trace is giving you the probability that when you take this guy in the input and this guy in the output, that you will observe a photon at the end of the day transmitted. That's the physical meaning of it. So sort of the probability that the input becomes the output. All right, so this is my only mathematics slide where there are some formulas. Sorry for this, even though it's only one, but it should be just fully relaxed talk. But I have another example of this, of the usage of trace in physics, and this is teleportation. So teleportation is probably, I don't know if this is a proper generation, actually, frankly speaking, but in my times, teleportation was mainly seen in the Star Trek, and it looks like this. So do you know what a teleportation, or is there anybody who doesn't know what a teleportation is? Or what is it used for, at least in principle and stuff? Everybody knows. So in principle, there is on Star Trek, on the spaceship, they had this device, teleporter, and when you want it to be in some distant location, doesn't matter how distant, actually, pretty cool device. Doesn't matter how distant your sort of destination is, you just go to this device, they will turn on some button, and you will be dematerialized. And then you instantaneously arrive at your destination you would like to be, and you will be materialized at that location. You do your business there. And then when some creatures want to harm you, because humans never harm other humans, right? When some creatures want to harm you, you press the button over here, you're dematerialized in that location, come back into your teleporter. There's an obvious problem with this. How the hell are you moving these guys faster with the speed of light, right? If it's really a far, far distant location, that's against physics. You can't move this. But there is something like this in quantum mechanics, which of course is consistent with the fact that you can't transmit anything, matter, information with the speed of light. And so people call this quantum teleportation. It goes like this. So what you need for this guy to happen, to operate, for this protocol to operate, is that you need certain special objects. And these objects are like your teleporters. But the difference between Star Trek teleportation and this teleportation is that you already have to have a teleporter at a distant location. In Star Trek, there was nothing, and these guys just emerged out of nothing, right? So, you got it? Am I speaking too fast? Sometimes I speak too fast. I am. It's okay. Okay. So you have a part of your teleporter is already at the place you want to teleport yourself. This is yourself, or myself. So of course, to simplify this whole picture, for the moment, let's just think that it's not really myself, which is like zillions of atoms, but just one photon polarized. And what I want to do, I want to bring, because I just talked about polarization, I just want to bring polarization of this photon onto polarization of this distant photon. So note that this polarization, it can be anywhere in the plane, right? It's described by a continuous, sort of infinite number of bits, continuous parameter, an angle in the plane. But what this stuff allows you to do is that you're taking your teleporter, you put your particle in the teleporter, something happens here, measure some sort of measurement, and then when you send only 2 bits, which are related to the measurement outcomes of this teleportation, sort of what happens in the teleporter to this state, you can apply certain treatment to the other side of the teleporter to see, and in the end of the day, you will see that this guy is exactly the same polarization as the initial one. There is a certain protocol that achieves this. So it's cool because you transmitted 2 bits to the other part, to the distant part, but you sort of, in a way, you now have access in, well, it's a continuous variable in a way which has just shifted to the other side. So imagine now that somebody is giving you this device. Would you like to use it? Well, I guess the first point, at least what I would ask to myself, okay, how reliable this is, right? You really want to make sure that things go right with this device, that what you put in really goes on. Because there is this case Douglas Adams reported in his restaurant at the end of the universe. This is his poem. I teleported home last night with Ron and Sid and Meg. Ron stole Maggie's heart away, and I got Sydney's leg. You don't want that to happen to you, right? This is essentially the reason why there is only a face of Douglas Adams shown here. So how do we deal with this? We have to check whether this teleportation device that somebody is claiming is really teleporting well. How do we check this, that it's really teleporting well? And this is where trace comes in, because there is this idea that we can actually figure out what the trace at the output, let me come back to this output. So we can actually really measure exactly what is exactly the polarization in this case, or what exactly is the state of this photon C. And the idea is just the same as the idea of the tomographs people do to other people, or medicine doctors do to their patients. So when this is a patient, and you want to know what's inside this guy, you want to know its state, you will take a picture of him at different angles. And then from this, if you can calculate it's the CT, computed tomography. You can calculate what's inside this body at certain points. And then the very same idea works for quantum mechanics. So what you have, if you want to learn what's inside, what has been produced there, if you want to learn this state, what you can do, there is always a certain set of measurements. And these are described by this sort of matrices over here. And we know that the probabilities are given by the trace. So there is always a set of measurements which will allow you at the end, if you know the probabilities of their outcomes, to reconstruct your state rho. So in other words, this is where trace comes in, because in practice, photons get transmitted or not, and you get a probability for this you can measure. This will be some number. You put this number on the left, you know more or less what you're measuring, so you know this matrix here, and you have a set of these trace equations, then you can solve it for rho, and you know what you're doing. You know what is the state of this teleported thing. That's the idea here. So I know it's pretty late, but maybe this will be 2 last slides. So I actually had a look into, so has anybody recently realized teleportation? And the answer is yes. And there is an amazing experiment just published last month where people have done this. So they teleported, exactly what I told you. They teleported polarization of a single photon along the distance of almost 150 kilometers. So yeah, that's sort of an example of a cool physical experiment, I guess. And what these guys were doing, they really wanted to check how well this 150 kilometers teleportation is working. So they would use these trace equations to figure out what's the state of the final photon over here. Now, there are 2 reasons, actually, why this is done here. So you see it's at La Palma and Tenerife, which is the Canary Islands. So reason number 1 to do this experiment, it's a cool place. Right? So you take your data.
What is a
Yeah. Quantum
quantum channel?
channel is a photon from a specially prepared source. So quantum channel is nothing else but, actually here it's just air. It's just air through which a photon from a very specially prepared source propagates. It's called quantum because this very specially prepared source. It's not a device. It's really just the air. So this experiment is done in free air. I think at night, because otherwise there's zillions of other photons that matter. But from stars, you don't have so many. So you do this sort of stuff usually at night, I guess. And then it's really so this is the second reason, sort of, why this is done there. Because normally, so you use telescopes to send these particles from one place to another. And normally the telescopes people built, of course these telescopes were built like 20, 30 years ago. No one was thinking about quantum teleportation at that time. Yes, exactly. So one of these particles has to be entangled with another one. That's where the quantum channel comes in, because it's sort of in distance quantum.
And how do you produce that? How do you basically separate the different places?
Oh, the entangled sort of these photons, they are entangled in polarization. Because I want to teleport to polarization, that's why I need to use entangled photons in polarization. So they are produced in certain crystals, in a way naturally. So there are certain crystals with the property that they only produce pairs of photons, first of all. So never 3 photons emerge out of this stuff, or 1, which is good for this. So just pairs of photons. And the probability that actually 2 pairs emerge is also pretty tiny. So this will a little bit mess your data, but it's tiny, so you don't really care so much. And these photons, okay, it's like this. Actually, this crystal, this process happens in crystals, and when you pump it with a laser, photons will emerge here or here because you have to satisfy conservation of momentum. So if you have one photon emitted towards here, the other one has to be emitted here because they should sum up to the initial momentum of the pump. And second thing is that the energy, it actually turns out that for some reasons, for some other conservation principles, these photons are always emitted in some sort of cones. So this is when you make it. So there will be a cone over here and another cone over here. And then actually it turns out that this photon has to be always on another cone, something like this. And then photons, because of these other conservation laws, these photons are always polarized in one way. These photons are always polarized in the other way. Sorry, I'm going into these details. Just 1 minute. And you can really check these guys are perfectly well polarized. But when you look into these points, here and here, this is the interesting physical situation. Because what can happen is that this photon is H polarized, but the other one has to be V polarized because they are always emitted on they always have opposite polarizations. But also, you don't know, right? It can also be that this guy is V polarized and this guy is H polarized. And it's really fundamentally impossible to figure this out, and this is what entanglement is. It's sort of a situation where you have 2 alternatives, And you just can't distinguish them. Here, HV, VH. This is the state which is useful for teleportation. OK, so yeah, so they have done this experiment. And actually, so the last thing which I wanted, second reason why they did it here, is that these telescopes were built a long time ago, and normally people just build telescopes to look at stars and look into the universe. But nobody really, I think, fully understands why. The telescopes which were built over here can really look on the ground. So they can just really make these two telescopes sort of talking to each other. And this is how this is realized. So I guess probably this sort of stuff is, this sort of stuff is meant to mean a telescope. OK, at the end of the day, what these guys find is exactly what I showed you before, is that they input different states to this teleportation device. They are somehow, this H means, for example, that it's a photon whose polarization oscillates in this plane. V means that it's a photon whose polarization oscillates in this plane. And at the end of the day, they use this, they have a results, measurement statistics on the teleported side. And from this, having this many trace equations, they can reconstruct what's the state on the teleported side. And this is what they find. So in principle, it should be that this is 1. But you see, the blue stuff is what they have measured. It's almost 1. Pretty good here. So it's this 1. It's like 1, 0, 0, 0. It's exactly this stuff here. So then this guy, it's almost really good, right? So this is a little bit worse here. So I would still think over whether I want to use this device or not for teleportation. There is a risk of getting someone's leg. And yeah, so the trace is used here to calculate this, to calculate how good your state is as compared to the initial state, in a way. And I guess these guys are actually density operators, density matrices. So you can find them out from experimental probabilities, but they are not, it's not trivial in a sense. It's pretty easy, but it's not immediate, right? You don't measure, so this stuff is not something you can just measure. You actually measure probabilities, and from them you can figure out, you can make some calculations to calculate this guy. OK, I had some more stuff, but I think it's pretty late, so I just do it for the summary. I just go for the summary. So we sort of care about trace in quantum mechanics because it gives you probabilities of the results in quantum experiments. In quantum mechanics, first of all, the trace is a property of a matrix. And it turns out that matrices are a useful tool to represent certain physical states, such as direction of polarization. And especially in realistic systems, then you really have to go to matrices. There is no, we don't know at least better ways of doing it than really consider matrices. And then this trace is important because it links your theory, it links your mathematics to what happens in the lab. And the exemplary applications of trace is to prove that we actually have done what we promised. So I have teleported something. I promised that it's a good teleportation. You can then use trace to verify that it really is what you have done. Or you can also think about it. You can use it to compare states because of this. So idea is that, as I told you, trace is like a probability that the input becomes an output. So if input is the same as the output, this is 1, right? Because they are just the same. So that's how it's sort of roughly the idea that we can use trace to compare different states. The number which comes out is telling us how close these two matrices are with each other. OK, so that's all I wanted to say. Thank you very much, and waiting for questions, if you have any. Yeah. Maybe put this guy on. It's a lovely poem, really. Have you read this? So this is the guy who wrote so this first book is The Hitchhiker's Guide to the Galaxy, which is pretty nice. It's just nice. It's a nice reading. It's full of this sort of mess. Yes. Oh, yes. You can. So you see, you can teleport these quantum states from one place to another. So you can teleport also the states of massive particles. People have and this has been done experimentally. People have teleported states of atoms into other atoms, and also states of atoms into light, which is pretty strange. But at the end of the day, from quantum perspective, so say this is a two-level system I want to teleport. In the atom case, this can be a spin. But there is a really one-to-one map between every two-level system in the universe. So you can map a spin of a particle into a polarization of a photon. There is a one-to-one map between these guys. So I guess just for fun, people teleported spins of atoms into polarizations of light. But yeah, I guess this is really important that there is no dematerialization in this quantum teleportation at one point and some sort of materialization of objects in the other spot. So if I would like to teleport myself, there has to be particles which are in me, ready in the spot I will be teleported to. And then I take the teleporter and do something on me. I vanish here, essentially. The state of me is really not interesting. But on that side, there will be me, if you apply certain treatment. This is, no.
Should be reconstructed somehow.
Yes.
It's a bit tricky because
Yeah.
when you explained that, I was thinking about, if this is the same individual photo. But then I realized
it's not.
It might not be the right question because we are dealing with probabilities. And what exactly is the
Yes.
photo?
Or yes, what exactly are you, right? If I teleport myself over there, it's a completely different set of atoms.
But there is the question of the soul. If you believe in that.
Exactly, and that's where I was aiming, right? So now it's exactly this question, right? I guess it's beyond physics in a way. Do you really believe that this teleportation, that the effect of this teleportation of me is me, right? So if you believe that there is something immaterial, something extra to quantum states, this is not you. But if you are sort of materialistic view, if you have materialistic worldview, that's you. Because there's nothing else in the world except these quantum states.
There will be some other theory replacing or extending quantum mechanics.
Yes, must be something. I think so, yeah. Well, yeah, some stuff is still, so for example, time is strange. So there are things which are strange in quantum mechanics.
Might also be
I think there will be some replacement.
this book of Norbert Wiener.
Sorry, don't know.
He's invented the word cybervectors. And
Okay.
one of his last chapters he mentioned that probability might not be the right form to quantify what we call chance.
Interesting. Yeah. Note that everything that quantum mechanics predicts are probabilities, so sort of. Yeah, but this is a good. But you see, imagine I give you this polarized photons like this, right? And then I measure it at some 45 degrees. So the chance that it goes through is 50-50, right? So what you can say so I just finished my thought. So what you can say in quantum mechanics is that in the infinite sequence of these experiments, there will be equal number of transmissions and equal number of not transmissions. That's it, finito. But maybe there is some order in this sequence, actually. I don't know that, right? The quantum mechanics doesn't say a word about it. But, well, yeah, maybe there is, I don't know.
And they are using Hamiltonians in this.
What do you mean? Yeah. Yes, we use Hamiltonians, indeed.
Everything is reversible.
Yes, in this sense, yes. So quantum state at one point of time is sort of deterministically propagated to another quantum state at some time, and you can also do it back, and that will be, it's deterministic. But still, there are many observables which do not commute with a Hamiltonian, for example. So why is that so important? Right? Because in classical physics, everything commutes in a way.
Because you actually have rationality. In the real world, time isn't reversible.
Whoa, how do you know that? Right. On the basic, in quantum mechanics, on the basic scale, it is believed that actually, the time evolution is reversible. But
Once again, with some probability. Because otherwise you violate the law of thermodynamics.
well, and then I wanted to say that this, for example, directionality of time, maybe it's just a sort of statistical law. Well, I don't know. Now we are going going far. But so to derive second law of thermodynamics, I guess it's really sufficient for you to look at statistical mechanics, right? And the basic, and whether the probabilities which
if you look at particles, then you have violations of the second law, because this is in the mean.
Yes, agreed, yeah. But I guess this stuff can even be observed, probably. Maybe people have observed them.
Further question? Okay, so there's free refreshments outside.
Ah.